Somewhere in southern China, there's a road that hangs 565 meters above a river, high enough that commercial aircraft occasionally pass underneath it. And the first time you stand on it, your brain simply refuses to process what your eyes are telling you. Solid asphalt, painted lane lines, guardrails, everything a normal road should have, suspended in open air above a gorge so deep that the river at the bottom looks like a thread. This is taller than the Eiffel Tower. Not almost as tall. Taller by a wide enough margin that if you laid the Eiffel Tower on its side at the bottom of this canyon, it still wouldn't reach the deck you'd be driving across. For most of human history, a gorge like this one was simply the end of the conversation. You didn't cross it. You went around it, however long that took, however many mountain switchbacks it demanded, because nature had drawn a line here that engineering hadn't yet found a way past. And then, in the span of about 5 years, a small province in southern China decided that line no longer applied to them and built one of the most extreme pieces of infrastructure on the planet directly through it. Somewhere in this story, there's a 3-centimeter mistake that almost derailed the entire final phase of construction. A night when the bridge itself started making a sound nobody expected, and a single number from opening. A week that says more about what this structure actually means than any measurement of height ever could. By the end of this, you're going to understand exactly what it costs, in money, in years, in raw human nerve, to hang 10,000 tons of steel in midair and convince it to hold still. To understand why anyone would attempt this, you have to understand what Guizhou province actually was before this bridge existed. This is one of the most mountainous, most isolated regions in all of China. A landscape of endless limestone ridges and plunging gorges that made roads almost pointless. Because the moment you finished paving one valley, another cliff face stood in your way. Millions of people lived here, effectively cut off from the rest of the country. There wasn't a single expressway anywhere in the province until the year 2000. Think about that for a second. An entire province, home to millions of people with no fast route in or out of it as the 21st century began. China's government eventually made a decision that sounds almost stubborn in its ambition. Connect. Guizhou properly, no matter what it cost, no matter what the terrain demanded. And almost immediately, that decision ran headfirst into one specific obstacle that had already defeated 13 straight years of highway planning. A single gorge cut by the Beipanjiang River, so deep and so violent in its geometry that every conventional bridge design engineers threw at it simply failed before it ever left the drawing board. You might be thinking, why not just build a normal bridge and get it over with? The honest answer is that a normal bridge cannot exist here. Standard designs rely on piers, rising up from a riverbed or a valley floor, something solid and reachable to plant a foundation on. This gorge offered nothing like that. Sheer cliff walls dropping hundreds of meters to a river far below, with no practical way to get heavy equipment down to build conventional supports, and wind conditions at that elevation violent enough to tear apart designs that would work perfectly fine anywhere else. Engineers spent 2 full years just studying the site before anyone was even allowed to propose a design, and the data they collected during that period was, by any reasonable standard, terrifying. Wind gusts recorded at up to 140 kilometers an hour ripping through the gorge at deck height, strong enough to make a conventional structure not just uncomfortable to drive across, but structurally unsafe. For 13 years, this single gap in the landscape had beaten every plan put in front of it. It's worth pausing on what 13 years of failure actually meant for the people living around this gorge, because it wasn't an abstract engineering delay. It was 13 more years of a 5-hour mountain detour for anyone who needed to reach a hospital, a market, or a relative on the other side. Families on opposite sides of this canyon were, in practical terms, closer to strangers 100 kilometers away than to neighbors who happened to live on the wrong cliff face. Children were sometimes boarded at schools during the week rather than making the trip home daily. Emergency vehicles simply couldn't reach parts of the region fast enough to matter in a real crisis. When you hear that a province had no expressway at all until the year 2000, it's easy to let that fact slide past as a statistic. It shouldn't. It means an entire generation of people grew up measuring distance not in kilometers, but in hours of switchback driving, with a gorge like this one standing as the single largest obstacle in almost every version of that math. That is, the weight sitting behind every design meeting, every failed proposal, every year this project didn't move forward. It wasn't simply a matter of national pride or a record to chase. It was about whether millions of people would keep living lives shaped entirely around a canyon they couldn't cross. Then, in 2011, one engineer proposed a solution radical enough to actually work. Forget trying to support the bridge from below entirely. Build 2 towers directly out of the cliff edges themselves and suspend the entire deck from cables strung between them. A cable-stayed bridge anchored not in a riverbed but in solid rock, hundreds of meters up on either side of the void. It was the kind of idea that sounds almost too simple once you hear it, and almost impossibly difficult once you actually try to build it. Construction officially began in November of 2011, and the difficulty announced itself immediately before a single tower had even started rising. The very first question was the most basic one imaginable. How do you get workers down to a cliff ledge that has no road, no path, nothing but sheer rock, to start building a bridge foundation? Every single anchor point for those foundations had to be drilled by hand directly into solid rock, because there was no way to fit conventional machinery onto ledges that narrow, that exposed, that far from anything resembling flat ground. Standard cranes were useless here too. There was nowhere to position them, nothing solid enough nearby to support their own weight, so engineers had to design an entirely separate piece of infrastructure just to move equipment and materials across the gorge. A temporary cross-gorge cable system, essentially a construction-grade zipline strung between the two cliff faces, before the real bridge had even begun, just to solve the problem of getting tools from one side to the other. Before any of that could even function, a road had to be physically carved into the cliff itself, and the only way to do that at this scale was with controlled demolition. Roughly 200 separate calculated explosions, each one precisely planned, used to blast a usable path directly into the rock face. After every single blast, geologists walked the newly exposed rock inch by inch, checking for hidden weaknesses, because a hairline fracture nobody caught in year 1 could become a catastrophic failure by year 4, buried under thousands of tons of concrete and steel with no way to inspect it again. From that point forward, 2 separate construction teams worked from opposite sides of the gorge simultaneously, racing toward each other across 700 meters of empty air with nothing yet connecting them but a shared blueprint and absolute trust in each other's math. Each tower's foundation anchor had to be drilled 15 meters straight down into solid bedrock. No shortcuts, no exceptions, because everything above that point, every ton of concrete and steel, and eventually every vehicle that would ever cross this bridge depended entirely on those 15 meters holding. It took 8 brutal months of continuous drilling and preparation before both foundation pits on either side of the gorge were finally ready to receive concrete. And when that pour finally happened, it happened the same way the raft pours happen on every extreme project like this one, all at once, without stopping. 15,000 cubic meters of concrete per tower foundation poured in a single continuous operation, because stopping partway through would leave a weak seam buried permanently inside the one component the entire bridge would eventually hang from. Inside that concrete sat a cage of steel reinforcement so dense that workers described barely being able to walk through the rebar grid before the pour began. A skeleton built to be trusted with 10,000 tons of steel deck hanging from cables anchored directly above it for the rest of the bridge's operational life. Then came the part that should genuinely stop you. Each tower didn't rise from flat, prepared ground the way a normal skyscraper does. It had to grow directly out of the raw edge of a cliff, on a footprint that was itself irregular, exposed, and hundreds of meters above the gorge floor. Engineers used a self-climbing concrete formwork system that rose roughly 4 meters every single day, the relentless mechanical rhythm of pour, cure, climb, pour again, repeated day after day, regardless of what the mountain weather was doing. Every worker platform at that height had to be fully enclosed, sealed against wind strong enough to physically throw a person off an open ledge. Because at these elevations, the same gusts that had terrified engineers during the 2-year survey phase were now blowing directly across active construction sites with men standing on them. Tower 1 reached 100 meters in just 62 days, an almost unbelievable pace given the conditions, and every single meter of that climb required a laser survey check, because a vertical error of even 1 degree, left uncorrected, compounds catastrophically over hundreds of meters. If the tower tilted even slightly out of true and nobody caught it early, the entire section built on top of that error would eventually have to be scrapped and rebuilt. While Tower 1 climbed, the crew on the opposite side of the gorge was already 40 meters ahead of them, an unspoken competition playing out across 700 meters of empty canyon air. Winter hit in 2012, temperatures dropping below freezing on cliff faces that offered no shelter from the wind, and the work never stopped, because a project moving at this pace had no schedule margin to lose to weather. Inside each rising tower, engineers embedded a system of pre-stressed steel cables designed to hold the concrete permanently under compression, reinforcing it from within against forces that no amount of raw concrete mass alone could resist. Every computer simulation the team ran against this design predicted the same outcome. It could withstand anything the gorge's brutal wind patterns were capable of throwing at it. Eventually, both tower tops rose level with the rim of the gorge itself, and the final concrete cap on each tower had to be positioned within 5 millimeters of its exact target location. A tolerance, measured in millimeters, applied to a structure that had just climbed nearly 200 meters out of a cliff face. Both towers were completed in 18 months, 392 meters of concrete combined, rising out of solid rock on opposite sides of a void that, even now, with both towers standing, remained completely empty in between. That emptiness was the next problem, and it turned out to be the single most technically demanding phase of the entire build. Each tower top was engineered to hold 56 individual cable anchor points, collectively rated to handle 4,000 tons of force. But before any of those cables could carry real load, someone had to get the very first thread of steel across a 720-meter gap with nothing underneath it but 565 meters of open air. The solution was a helicopter, hovering directly over the gorge in crosswinds reported at 80 kilometers an hour, while workers on either tower carefully attached the first thin pilot wire that would eventually be used to haul the real cables into place. It is difficult to overstate how much skill that single maneuver required. A pilot holding a hover in violent, unpredictable mountain crosswinds directly above a 500-meter drop, while a construction crew threaded a steel line through the aircraft's reach with zero margin for a mistake. Once that first cable was secured, the real installation began, and each one of the 56 cables per tower was built from 109 individual steel wires, twisted together under exact calculated tension. Every single new cable that went in changed the tension distribution across every cable already installed. Engineers described it as tuning a giant instrument, where adjusting one string shifts the pitch of every other string on the frame, except here the instrument was 720 meters wide, and the stakes for getting a note wrong were measured in structural failure. Rather than a bad chord, each cable had to be tensioned to within 1% of its precise target load, and as the cables tightened one by one, they physically pulled the growing deck sections upward into alignment, the bridge quite literally assembling itself into shape through calculated tension rather than brute placement. It's worth stopping here to acknowledge what that 10-month deck building phase actually asked of the people doing it, because the finished bridge, smooth and level and lined with paint, erases almost every trace of it. Welders spent full shifts working 565 meters above a river, tethered to a structure that was, by definition, still incomplete and still settling under its own accumulating weight. Inspectors crawled through sealed steel boxes barely wide, enough for a human body, checking welds by flashlight in enclosed spaces where a mistake wouldn't announce itself until years later, under load, far from any easy repair. Crane operators lowered 100-ton prefabricated deck sections into position with tolerances measured in millimeters, in crosswinds that regularly exceeded 100 kilometers an hour, fully aware that a single miscalculated swing could undo months of upstream work in a matter of seconds. 3,500 workers moved through this project. Across 5 years, many of them living in temporary camps carved into mountainsides far from home, repeating some of the most physically demanding and mentally the tension percentages, the millimeter tolerances, the deflection numbers, represents thousands of individual decisions made by people standing somewhere genuinely terrifying, getting it right anyway, because getting it right was the only acceptable outcome. Even with the deck physically connected, the bridge was still a long way from being something you could drive across, and the final stretch of work moved with the same relentless precision as everything before it. Before any road surface went down, crews laid a 20-centimeter reinforced concrete base across the entire deck. Paving the driving surface itself took 6 continuous days, running 24 hours a shift, because a project on this schedule had learned by now that pauses cost more than exhaustion did. Every safety system went in at once, running in parallel rather than sequence. Crash barriers, roadway lighting, lane markings, signage, all installed simultaneously to compress the final timeline as tightly as possible. Special expansion joints were built into the deck to allow roughly 60 centimeters of movement, because a structure this size does not stay perfectly still. Guizhou's seasonal temperature swings caused the steel deck to physically expand and contract by close to half a meter over the course of a single year, and without joints engineered to absorb that movement, the bridge would eventually tear itself apart from thermal stress alone. To keep watch over all of it permanently, engineers embedded roughly 600 sensors throughout the structure, continuously reporting the bridge's structural health in real time to a dedicated control room, where the entire span is monitored essentially the way a hospital monitors a patient's vital signs, around the clock, indefinitely. Before opening day, the bridge had to prove, under real physical load, that every one of those years of simulation had actually been correct. 80 fully loaded trucks, each carrying maximum legal weight, drove onto the deck simultaneously in a single coordinated load test, and engineers watched the structure deflect exactly 45 millimeters under that weight, precisely what the computer models had predicted years earlier, down to the millimeter. Additional tests sent trucks across at varying speeds to measure the deck's dynamic. Vibration response under moving load, and the wind behavior recorded that day matched the original 2-year survey data almost exactly. Years of research, modeling, and calculation, all validated in the span of a single testing day. When the bridge's lighting system was switched on for the first time, villagers in the valley far below reportedly stopped what they were doing just to stare upward at what looked, from that distance, like a glowing ribbon of light, suspended impossibly in the dark sky above them. Inspectors then walked the entire length of the bridge by hand, checking every centimeter before certification, and the resulting final inspection report ran to roughly 4,000 pages, every calculation checked and then checked again. After 5 years of continuous construction, the Beipanjiang Bridge was formally declared complete and structurally sound. 3,500 workers had built it, and every one of them was given the chance to walk across their own creation before it opened to the public. Final certification came through from Beijing. Construction complete, safety verified, bridge approved for use. On December 29, 2016, the ribbon was cut at exactly 10 in the morning, and the world's highest bridge officially opened to traffic. The first official convoy crossed the entire gorge in 4 minutes. The old mountain route it replaced had taken 5 hours. Elderly villagers who had spent their entire lives walking narrow mountain paths around this exact gorge reportedly wept as they watched the crossing happen in minutes instead of an afternoon. On opening day alone, more than 3,000 vehicles crossed the bridge, and within 24 hours, images of the completed structure had reportedly reached over 500 million people online worldwide. One local business owner later reported that the new crossing cut delivery times by 97%, a single number that captures, better than almost any engineering statistic could, what this bridge actually did for the people who live beneath it. Guinness World Records eventually confirmed it officially, the world's highest bridge, 565 meters above the river below. For 13 years, engineers said a crossing here was impossible. For 5 more years, 3,500 workers proved otherwise. 1 hand-drilled anchor, 1 poured foundation, 1 tensioned cable, 1 welded joint at a time until a gorge that had cut off millions of people for generations simply stopped being a barrier at all and became, instead, one of the most extraordinary things humans have ever built above open air. Put this bridge next to almost any other famous crossing on Earth, and the comparison starts to feel almost unfair. The Golden Gate Bridge, for all its fame, sits roughly 70 meters above the water beneath it. The George Washington Bridge clears the Hudson by about the same margin. Even most of the tallest bridges built specifically for dramatic mountain terrain rarely approach half the clearance engineers achieved here. At 565 meters, the deck of this bridge sits high enough that low-flying aircraft have genuinely passed beneath it, a detail so unusual that most people hearing it for the first time assume it has to be an exaggeration. It isn't. And unlike a bridge built across a river in relatively cooperative terrain, every meter of clearance here came from a canyon that had already rejected 13 years of competing designs before this one succeeded, which makes the final number less like a record chased for its own sake, and more like the byproduct of simply solving the actual problem in front of them as honestly and as precisely as the terrain demanded. There's also a version of this story that has nothing to do with cables or concrete at all, and it's arguably the more important one. Before December 2016, a 5-hour mountain crossing wasn't an inconvenience for the people living around this gorge. It was a structural fact of daily life, shaping which hospital you could reach in an emergency, which market you could realistically sell goods in, which schools your children could attend without boarding away from home. A 4-minute crossing doesn't just save time, it rewires the entire geography of opportunity for everyone living within reach of it, which is likely a large part of why elderly villagers who had spent decades walking those old mountain paths were reportedly moved to tears the first time they watched a car cross in minutes instead of an afternoon. Engineering projects at this scale tend to get remembered for their numbers, the height, the tonnage, the record. But the number that arguably matters most here is the 97% cut in delivery time reported by a single local business owner in the weeks after opening. Because that number is the one that actually changed how people in this province got to live their lives. The height made headlines. The 4-minute crossing is what made the difference.